Alright everybody, let's talk about the mathematical representation of a traveling wave, traveling sinusoidal wave. So if we have a rope, let's say that we attach to a wall and then we grab one end of the rope and we shake it up and down, we can produce a pulse like this with that kind of shape, and that pulse, as we know, is going to propagate down the rope. Sometime later the pulse is going to be somewhere there. Now if we shake that rope in a different way, maybe in a more smoothly or more fluid way, we can get the profile or the shape of the pulse to be different. Maybe we can get a curve, something like this, propagating down the rope. Now, if we shake that rope in sort of a random way, up and down in a random way, what we get is some randomly looking, random looking pulse that will propagate down the string. So the profile of the shape of the pulse or the shape of the wave depends on the specific way in which you produce the disturbance at one side of the rope. So the question is, if we shake the rope by using a harmonic oscillator, that is, if suppose that you had a spring and we put a mass attached to the spring and we attach the rope to it and then we push this oscillator down, for example, then the oscillator, the harmonic oscillator, which was discussed at the end of the last part of the semester of 24-25. So if this harmonic oscillator is attached to the rope, how is the wave that propagates in the rope? What does it look like? So the answer is that the wave that is going to propagate in this rope is going to be a sinusoidal wave. We're going to call it sinusoidal wave because if we take a picture of the wave at any given moment, it looks like a sine curve. So again, if the end of the rope is shaken as a harmonic oscillator or following the motion of a harmonic oscillator, if we manage to move that end of the rope in that specific way, that is, if the displacement of the end of the rope as a function of time is a sine function, or cosine, because the sine and the cosine functions are the same, except that they're just displaced with respect to each other. So if that's how we shake that rope, then we can expect to have a sinusoidal traveling wave propagating in this medium. So the displacement versus time function, which is a sine function, as I said, is going to describe the displacement of the rope as a function of time for any point on the medium. As the wave propagates through it, every single point is going to shake in the same way. It's going to go up and down, following the same kind of profile. So this function is clearly periodic, and the displacement of the rope at any given time, t, will be the same as the displacement of the rope at a time t plus capital T, where this capital T has been described before as being the period of the wave. So the wave that propagates is going to be periodic, and after t seconds, capital T seconds, the wave repeats itself. The oscillation repeats itself. So we call t the period of this wave. We can also talk about the period as being the distance or the time that it takes for a particular point in the rope to be at its maximum displacement and then go back to the same maximum displacement. Now the profile of the rope, that is when we take a snapshot of these ropes, again going back to the example of the wave moving in a rope. So when we take a picture of this rope, the displacement versus position along the rope is, as we said, is going to be also a sinusoidal function. And the displacement at any given point x will be the same as the displacement at a point x plus lambda, or lambda, you can see there that it's a distance. Also in previous videos we talked about lambda as being the distance between a crest and an adjacent crest in a traveling wave. So lambda is the wavelength of this wave. So mathematically speaking, the periodicity of the wave in position can be described this way, by saying that the displacement of the wave, which is a function of x and time, that is any particular point on the rope, it can be described by position x, and then at any particular time we describe that time with t. So the displacement of that point at a particular position and time is the same as the displacement at some other point on the rope that is a distance lambda away from it. So that's a sort of a fancy way of saying that the wave, the sinusoidal traveling wave, repeats itself over a distance of lambda meters. But it also repeats in terms of time. After t seconds, any point on the rope is back to whatever it was doing before. So the displacement of any point x and t is equal to the displacement of that point x, but at a time t plus the period of the wave. So we say that the wave is also periodic in time, that it repeats itself after t, capital T, seconds, where t is the period. So a function that has these properties, a function of x and t that has these properties, you can see it there, is a, which we're going to call the amplitude of the wave, a sine of 2 pi over lambda times x minus 2 pi over the period times time plus phi naught. I'll explain in a minute what phi naught means. But notice that this function satisfies the fact that the displacement as a function of time is a sinusoidal function, which we said this is how a harmonic oscillator moves. So this is satisfied by the function inside the red square, because as you can see there, this is a sine function. If we leave x fixed, then it's a sine function that depends on time. So that would give us the profile that we said it would have. Also, this function satisfies that the displacement as a function of position is also a sinusoidal wave, because as you can see there, this function sine is going to, or has as an argument, x. So if we leave t alone, we see that as x changes, the function displacement is going to change as a sine function, which has the property that we said should have. And then the one thing that we need to check is the periodicity. Is this function that is inside the red rectangle, is it periodic in position? So you can check to see if by replacing x with x plus lambda in that function, we get the same value of the function. So plug in x plus lambda instead of x. So we got a sine of 2 pi over lambda multiplying x plus lambda, and then the other stuff inside the argument of the sine function, which we don't care because we're only changing x right now. So we get a sine of 2 pi over lambda x, and then 2 pi over lambda times lambda, plus the other stuff inside and notice that what just happened there is that lambda, there was a lambda in the denominator and a lambda in the numerator, and those two lambdas cancel, and we get a 2 pi showing up inside the argument of the sine function. We can, this 2 pi, we can get rid of it and get that the displacement of the wave at x plus lambda is the same as the displacement of the wave at x. And the reason why we can get rid of that 2 pi is because all trigonometric functions are periodic in 2 pi. So after 2 pi, all trigonometric functions, sine, cosine, tangent, etc., they all repeat after a period of 2 pi. So if you take the sine of theta and you replace theta with theta plus 2 pi, the value of the sine is unchanged. So it doesn't matter if you add any multiple of 2 pi in the argument of a sine or a cosine or a tangent function, you don't change the value of the function because the function is periodic with period 2 pi. So we can get rid of that 2 pi, and as we said, we have proven that the function is periodic in position with a period lambda, the wavelength. Then we can also prove easily that the function is periodic in time, and that the periodicity of the function in time should be capital T. I'll leave it to you as a very simple exercise to prove that. Just replace for T, replace T plus the period, capital T, and you'll see that you get another, again, you get this 2 pi showing up, and you can get rid of the 2 pi, as we just discussed, and then you get that the function is periodic. The value of the function of t plus capital T is the same as the value of the function of t. So this is the mathematical representation of a traveling sinusoidal wave. Now this number here in yellow, 2 pi over lambda, we can assign a letter to it to just not always have to write the 2 pi over lambda, just to simplify things a little bit. So the value of lowercase k is defined as 2 pi over lambda. It has a special name called the wave number. So at 2 pi, the number 2 pi over lambda, we're going to call it the wave number. And this other value, 2 pi over the period, we're going to call it the angular frequency. We're going to give it the letter omega, just like the same letter that we use for rotational motion. But this omega stands for angular frequency. And as you can see there, is the same as 2 pi times the frequency, because frequency is defined as 1 over the period. So angular frequency, 2 pi over the period, or 2 pi times the frequency. Now the wave number, the units of the wave number, notice that will be radians per meter. So how do we interpret this wave number? What does it mean or signify? So remember that a complete oscillation corresponds to a change in the argument of the function by 2 pi. So 2 pi is one complete oscillation. So if we have a big k, that is if the wave number of a certain traveling wave is big, that means that we have multiple radians, that the wave is oscillating over multiple radians in a distance of 1 meter. So that means that the wave has a small wavelength, and that therefore the wave does multiple oscillations. Remember that the number of oscillations and the number of radians are related to each other. One oscillation is 2 pi radians. So a big wave number implies that the wave oscillates many times in a distance of 1 meter. Therefore, a small wave number implies that the wave oscillates or does very few oscillations in a distance of 1 meter, or it could even do 1 fraction of an oscillation in a distance of 1 meter. Now for the units of the angular frequency, those are radians per second, and the interpretation of this is that the angular frequency is telling us how many oscillations does the wave do in 1 second. It's similar, as you can see, since the angular frequency and the frequency are proportional to each other, then they're giving us basically the same kind of information. So if, for example, we have an angular frequency of 2 pi radians per second, since 2 pi is 1 oscillation, that means that this wave is doing 1 oscillation every second. And 1 oscillation in 1 second means that the period is 1 second. Notice that this is exactly what you get from this expression here, omega equals 2 pi over the period. If omega is 2 pi, then the period is 1. So for a wave that has a low angular frequency number, what that means is that the wave in 1 second doesn't go too far, doesn't oscillate very much. It just does maybe a fraction of a whole oscillation if the angular frequency is very small. If we have an angular frequency that is very high, what that means is that the wave does many oscillations. The wave goes from one point to it goes up, and then it goes down, and it goes up again, and it does all that in 1 second. So if a wave, any point in a wave behaves that way, if a point on that string goes up and down several times in 1 second, then we say that it has a high angular frequency. All right, so in using k and omega, we can simplify a little bit, writing the traveling sinusoidal wave. We can write it as a sine of kx minus omega t plus phi naught. Notice that this minus is the sign that needs to be used to describe a traveling wave to the right, and a plus sign is what should be used to describe a traveling wave that goes to the left. If you don't know why that is, remember that in your previous math classes, in algebra class, you learn that when the argument of a function f of x is changed by x minus a, if you subtract a, the whole function moves to the right by a distance a. And if you change the argument, if you add a to the argument of a function, you're moving the function to the left by a distance a. So the minus omega t and plus omega t are related to moving or what they're doing basically is moving the minus omega t is moving the function, the traveling wave is moving it to the right, and the plus omega t is related to the wave moving to the left. Now the velocity of a wave was discussed in previous video as lambda times the frequency. You can also write it as lambda divided by the period. Now if we use the wave number 2 pi over lambda, we can solve for lambda in terms of the wave number k. So lambda is, as you can see there, lambda is 2 pi over k. So we can plug that in there, and using the angular frequency, which is 2 pi over the period, we can solve for the period as being 2 pi over the frequency, angular frequency, and we plug it in there. And if so that gives us omega is going to the numerator, k stays in the denominator, the 2 pi cancels, and we get that the velocity of a traveling wave can also be written as omega divided by k, the angular frequency divided by the wave number. So we have several expressions here for the velocity of a wave. The top one in terms of lambda and the frequency, or lambda and the period, and the bottom one in terms of the angular frequency and the wave number. All right, there's only one thing left to discuss in the equation that gives us, or that describes a sinusoidal traveling wave, and that is this phi naught number inside the argument. This phi naught is called the initial phase, or also called the phase constant. So what this number tells us is in what part of the oscillation cycle the wave is at the specific point x equals 0 and t equals 0. So let me give you an example. Suppose that the wave that you are examining or studying at t equals 0, the wave looks like this. The displacement as a function of position looks like what you're seeing in the plot at the bottom. This is what's happening at t equals 0. So at x equals 0, notice that the displacement of the wave is maximum. So the displacement of the wave at t equals 0, x equals 0 is equal to a, the amplitude of the wave. So what is the value of phi naught that is consistent with this? So take a look at the equation on top, replace x equals 0, t equals 0. You get a sine of 0 minus 0 plus phi naught, so that's a sine of phi naught. And we know that this is equal to a. From the picture, we can tell that the displacement is the amplitude of the wave at that point. So a sine phi naught equals a, therefore sine of phi naught is equal to 1. And the only value that gives you the sine of a function being 1 is if the argument of the sine is pi over 2. So in this case, the initial phase is pi over 2. So if we know that the initial phase of this wave is pi over 2, we know how the wave starts. We know what the wave looks like at t equals 0 and x equals 0. Okay, so we know that the wave is going to be the oscillation of the point x equals 0 at t equals 0 will be at the top. It will be at the maximum amplitude when the initial phase is pi over 2. So that's why I said that phi naught tells us in what part of the oscillation cycle the wave is at the specific point x equals 0, t equals 0. If the initial phase is pi over 2, we know that the wave at x equals 0, t equals 0 is at the top of the oscillation. But what if the wave picture, the snapshot of this wave, looks like this? At t equals 0, notice that the displacement is 0. So what is the phase constant that is consistent with this? So if we look at the equation above, again, replacing x equals 0 and t equals 0, and also looking at the graph, knowing that the displacement is 0, we get 0 equals a sine of phi naught, which gives us two possible phase constants. 0, because sine of 0 is 0, but also pi, because sine of pi is 0. So which one is the correct one? So we have to think a little bit more about this. So if we choose the initial phase equals 0, the function d of x at t equals 0 is sine of kx. So sine of kx is the function that you get if you choose the initial phase being 0. And if you choose the initial phase pi, the function that you're looking at is sine of kx plus pi. Of course, there's an a multiplying, but that's not important right now. So which of these two functions matches the function that you're seeing depicted? Is the function there sine of kx, or does it look more like a sine of kx plus pi? So if you remember your trigonometric functions and the way that the shape that they have, you'll know that the function that we have there must be sine of kx, because the sine of theta starts at 0 and it ramps up towards reaching a maximum at theta equals pi over 2. So the function that we have here has the same behavior. It's crossing 0 at x equals 0 and is ramping up, going up. The function sine of kx plus pi looks like that, what you see there. It crosses 0, sure, sine of pi is equal to 0, but as you increase the argument of the sine function, if you go a little beyond the x equals 0 point, you're adding a little bit of phase. I wrote that as a delta number there, and notice that sine of pi plus some small angle is negative. That's because pi plus a little bit takes you to the third quadrant, and you know that the sine of an angle that is located in the third quadrant must be negative. So what that means is that the function, as x increases to the right, the displacement of this wave goes down as depicted in this picture. So that is not the behavior that we have here. That's not the behavior that I was showing you here. As you can see, the displacement as a function of x increases as x increases. So of the two values, 0 and pi, we figure out that what's consistent with the graph is the value of initial phase equals 0. All right. Let's take a look at another one. So, or summarize a little bit. So the first case that we discussed was the one on the left, right here. We said that if the traveling wave at t equals 0 looks like that, we have an initial phase or a phase constant of 0. Then we discuss that if the traveling wave looks like this at t equals 0, then the initial phase must be pi over 2, since it's starting at a maximum. Sine of pi over 2 is 1. Then we have this case. We just discussed this case where the this is what you would get if the initial phase was pi. And in this case, suppose that the t equals 0 displacement function has a maximum but negative in value. What is the phase constant consistent with this wave? The answer is the phase constant is 3 pi over 2. Notice that the sine of the phase constant, sine of 3 pi over 2, is minus 1, and that's what we have here. All right, so that's it for now. See you in the next one.